Hi everyone, we're going to do an example regarding drag force and differential equations. Let's look at the example. An object of mass m is launched from a stationary helicopter toward the Earth with speed v0, so that's our initial speed. It experiences a force of air resistance, F equals negative kV, where k is a positive constant. The positive direction of all vector quantities is downward. Now this is the reverse of what we usually see. We usually set downward as negative, but here they're telling us that it's positive and that upward is negative. The first question is to draw a force diagram for the object. Well, we'll start out with gravity. We know that gravity is mg. And then we've got this upward drag force that's changing as a function of velocity. I'm going to call it F drag, but you could call it F air, F drag, Fk, anything that indicates it's a frictional force that opposes motion. And its value is negative kV. Now let's look at a scenario here. I made a little video with a coffee filter. Coffee filters are great for showing this. That's a coffee filter falling, and I'd like you to notice that the coffee filter falls at a fairly constant speed. It accelerates at the very beginning, and then it falls at a constant speed. And I can prove that by looking at the graph of the vertical motion. In fact, let's go back to Notability. I've got a screenshot. Well, I did have a screenshot. My screenshot is gone. I'll take another one. Okay. There we go. Oops. Let's see if we can make this a little bigger. And get rid of that. Okay, here we go. Okay, so a couple things. What are we looking at here? This is a position. Come on. This is a... Okay, Notability. Notability. Help me out here. Really doesn't. Here we go. There we go. This is a position time graph. And in a position time graph, we know that slope equals velocity. So let me use a different color. So down here, the slope is constant, which means the velocity is constant. Another way to look at that in the second graph is a velocity graph. And look what happens. The velocity increases, and it increases in a non-linear way. Here, the slope is acceleration. And the acceleration is decreasing. And in fact, the acceleration decreases to 0. The slope here is 0. The velocity reaches a terminal value. And we can think of this, maybe negative 1.5 is like an asymptote. Can I remember how to spell asymptote? So this green line would never reach that asymptote. Now I'd like to make a note here that that's what I did in my experiment. I set it up the conventional way. But in this problem, they have told us to make it the reverse. So if we were to make down positive, what happens to our graph is it looks the same for a position time graph. It looks the same but flipped over the y-axis, or I'm sorry, over the x-axis. And here, this would be a constant slope. This is where we get terminal velocity. And then if I were to do the same thing for the velocity time graph, I'm going to put in a dotted line for my terminal velocity. And, oops. And so it's going to look something like this. Oops, don't touch. Okay, that should be a little straighter at the end, but I think you get the idea. Oh, by the way, these pages I'm passing here is a textbook explanation of the same problem, just in case you want to see a textbook explanation of the same problem. Okay, let's keep going. Let's find the terminal speed of the object. Okay, so to find the terminal speed of the object, I'm going to assume that happens when, I'm going to assume that the terminal speed happens when the drag force is equal and opposite to the gravitational force. Remember, the gravitational force is not changing, but the drag force will increase as the object speeds up. So we need the amount of the drag force to be equal to the amount of the gravitational force, or kV to equal mg, or terminal velocity would equal mg over k. So back to these drawings, this value would be mg over k. That's my terminal velocity and my asymptote. Okay, part C. Write and solve a differential equation to find the speed of the object as a function of time v naught, m, g, and k. Okay, so this is kind of an involved question in terms of calculus. And one moment, please. I need to find something here. There we go. And so what we're going to do is we're going to solve this problem, but I'm going to pause along the way and kind of think about some strategies for test taking and also for thinking. So the first strategy I'm going to do is think. And I want to make sure that I understand all my variables. So time, t, time is changing. Time is definitely a variable when we have moving objects. This v naught, though, this is initial velocity or initial speed downward. That's a given in this problem. Mass is also a given and a constant. G is given and a constant. And K is also a given constant. So V, M, G, K, those are all constants. And I want to keep that in mind when I'm doing calculus. Right? Right. Okay, so what I'm going to do next is I'm going to write and solve a differential equation for a velocity. And I'm going to start with Newton's second law. I know that the net force on this object while it's accelerating is equal to Fg, that downward force, minus the drag force. Now over here I'm going to write some substitutions I'm going to make later. Fg is equal to mg. The drag force, the amount of drag force, is kV. The net force, Newton's second law, is equal to ma. And then acceleration. Acceleration is change in velocity over change in time, or dv over dt. All right, let's jump right in. Instead of writing net force, I'm going to write ma. For Fg, I will write mg. For F drag, I will write kV. And now one more substitution. M times dv dt equals mg minus kV. Okay, now let's pause here and let's have a minor celebration, because we have written the differential equation. So we've done the first half of the question, and it took some thinking and some physics, but not a ton of calculation. Let's do one more step actually. Let's solve for dv dt. Okay. So that's great. But and we would get half of the points. Typically this would be a 4-point question, and getting it this far would be 2 out of 4. Now we're going to go ahead and solve it, and you're going to see that the amount of work it takes to get the other 2 points is kind of disproportionate. But we're tough, we're smart, we're strong. We are going to continue on anyway. Okay, so I'm actually going to go back a step here. And the first thing that I have to do to solve this is I have to separate the variables. So this is where it's really important to know which are my constants and which are my variables, because I can't separate the variables if I don't know what they are. It's also where understanding the graphs is really, really helpful, because when you can picture the graph in your head, oh, here's a picture, just like I drew, V and T. If you know velocity and time are your variables, that's really, really helpful and necessary. So I need to get V and T on opposite sides of the equal sign. Okay, so that's just some algebra. So I need to get the V's on the same side and the D's on the same side. So what I'm going to do is I'm going to multiply both sides. I'm going to multiply both sides by dt. So it cancels here. And I'm going to divide both sides by mg minus kv. Like that. Okay, so now what have we got? We have got that m dv over mg minus kv equals dt. Okay, we did it. We've got the v's on one side and we've got the t's on the other. I'm going to turn this around. I'm going to write dt equals m mg minus kv dv. All right, well, that's great. Now how am I going to solve this thing? It's got derivatives in it, and to undo a derivative, I need to do an integral. Right now, this is an indefinite integral. So the integral of dt is just t plus some constant. And on the right side, I'm going to have to use u substitution. And I'm going to set u equal to mg minus kv. And then I'm going to have to find du. Du would be 0 minus k dv, or negative k dv. So dv would be equal to negative k over du. And now I'm going to make my substitution. I'm going to factor out this m here on the top. I'm going to put it outside the integral because I know it's a constant. I'm glad I thought about that earlier. And I'm going to say 1 over u, because remember u was mg minus kv. And then instead of dv, I'm going to write negative k over du. Wait, I did that wrong. That's upside down. That didn't look right. Let's try that again. dv is du over negative k. Sorry, didn't mean to scare you there. Okay. I'm actually going to go ahead. I like to keep my projects neat as I go along, so I'm going to factor this k out. Okay, now I need to know how to integrate 1 over u, and that was one that you were supposed to memorize in calculus class. The good news is, spoiler alert, it's the natural log. If you didn't know that, you are allowed to use notes and references. So I would have a table of integrals handy. I also want to point out that this whole thing that we're doing is only worth 2 points. So I wouldn't, if this isn't your jam, I would do the stuff you know how to do first and then come back to this if you have time. And I don't even know if they're going to ask a question with this much calculus in it, but anyway, we hadn't done a lot of calculus, so I thought you could hear my voice doing some calculus and maybe you would find that useful. All right, so I'm going to keep going here. So t, that's time, plus some constant is going to be equal to negative m over k times the natural log of, oh, it's actually, sorry, sloppy on my point. The natural log of the absolute value of u plus a constant. And really you could combine these two constants into one and they'd be, you could put them on the other side of the equation. And then I need to substitute u back in. So I'd have the natural log of mg minus kv. Okay. Oh yeah, plus c. So that's pretty great. And now we need to solve this. And to solve it, we need to use a technique called exponentiating. Meaning we're going to do e to the something because we know e to the ln x equals x. And that will get rid of our natural log. Before I do that, I'm going to, just a little bit of housekeeping here. I'm going to multiply both sides by negative k over m. And that's going to give me negative k over mt equals the natural log of mg minus kv plus c. All right, now let's exponentiate. E to the negative k over mt equals e to the natural log of mg minus kv plus c. Okay, remember that if you have this, it equals that. Remember those properties of exponents? Okay, so this is going to be e to the negative k over mt equals mg minus kv times some constant, and this constant keeps changing, but I'm just going to roll with it. In the textbook version, it's a little more careful. It keeps track of which version of the constant it's on, but I'm just going to keep it as a c. It's a different c than it was before. Okay, now, well, I guess actually if you like, I think we're on C3 here. This would be C2 and so on. Okay, so now I could divide both sides by C, and that would make this actually the fourth version. And I'm going to get rid of the absolute value symbol. There are two solutions here. And we want the positive one. And now what I have to do is I have to solve for v. So I'm going to subtract mg from both sides. And then I'm going to divide by negative k. So I have c to the negative k over mt minus mg all over negative k equals v. All right, pretty great. Okay, we could clean this up a little bit. If we wanted to determine what c is, we could plug in at time equals 0, v equals v naught. So let's see, we've got c4 e to the, this would be e to the 0 minus mg over k, negative k, equals v naught. And now I'm solving for c4. Let's see. This is 1. So you could take that value and plug it back in to create the final value. V equals negative V naught K plus mg e to the negative K over mt minus mg over negative K. All right, that is a beast. And you can see how you wouldn't want to waste all of your time. This is going to be a very short test. You wouldn't want to spend too much time on this, especially if it's giving you heartburn. You would want to focus your time getting to here. See, this got us half the points, and all of this got us the other half. Pretty good, huh? Okay, let's finish this up. The acceleration of the object before it reaches terminal velocity is... it's positive. The acceleration is always positive. And if we go back to the diagram, if we go back to this, the slope here in this graph, the slope is always positive. It does until it gets to 0, but it's never a negative number. So that's that. And then we've already done this, but we'll just sketch it on this axis since it says to do it. Plot the speed of the object versus time. Okay, well, we know that there's a terminal velocity. The terminal velocity is mg over k, and we know that the velocity will approach that asymptotically, like with a limit as time increases. All right, I hope you find this helpful. Please reach out with any questions that you have, and I will talk to you soon.